We have so far discussed Lagrangian way of solving the problems of mechanics. Another most significant method of solving dynamical problems is due to Hamilton. Now we will study this Hamiltonian formulation of mechanics. Actually, we have studied that in Lagrangian formulation, the independent variables are generalized coordinates, which are denoted by qk and time t. The generalized velocity, which is denoted by qk dot, qk means generalized coordinates, and qk dot, actually qk dot, you know, this is dqk by dt. These are known as generalized velocity. And we have seen while the study of Lagrangian formulation that these generalized velocity also appear explicitly in the formulation. But since you may see this generalized velocity qk dot is simply the time derivative of generalized coordinates, so they must be treated ultimately as dependent variables, not independent variables. Actually, the viewpoint of Hamiltonian way is to remove this dependence and introduce a new independent variable, and that new independent variable is known as generalized momentum, and that is denoted by pk. So in Hamiltonian formulation, along with the independent variable qk, we will use an independent variable pk, which is actually known as generalized momentum. And actually this is not a dependent variable, it is an independent variable, that is its status is same as that of qk. And you know in Lagrangian formulation that the Lagrangian of the system, which is denoted by L, that L is actually the function of generalized coordinates qk, generalized velocity qk dot, and time t. In Hamiltonian formulation, instead of this Lagrangian formulation L, we use another function that is called Hamiltonian of the system, or you may also call it Hamiltonian function. It is denoted by h. And actually this h, which is called Hamiltonian of the system, Hamiltonian of the system, or simply Hamiltonian function, this h is actually a function of generalized coordinates qk, generalized momentum pk, and time t. So in fact we can say that there is just a change of basis. In Lagrangian formulation, the basis was what? In Lagrangian formulation, formulation, the basis is what? This is qk dot and t. So there is just a change of this basis in Hamiltonian formulation, and this change in basis is actually from this basis qk dot t to qk pk t. So this is just a change in basis, qk dot t. This is actually the basis of Lagrangian formulation. Lagrangian formulation. And this basis is changed into qk, pk and t. And these are in fact the basis of Hamiltonian formulation. This is basis of Lagrangian formulation, and this is basis of Hamiltonian formulation. Hamiltonian formulation. While we have studied in the previous lectures the meaning of this generalized momentum. Actually, the n generalized momenta are defined as what? In which way? Actually, the n generalized momenta are defined as, we define it pk equal to del L by del qk dot. We have already studied in previous lectures of Lagrangian formulation. So this is the definition of generalized momentum, and you can see from this definition that for each generalized coordinate qk there corresponds a generalized momentum pk. So if qk has, let us suppose, 3 values, pk will also have 3 values, because corresponding to each generalized coordinate there is a corresponding momentum coordinate. Thus, you can say that the mechanical state of a system can be described completely provided the qk and pk are given as function of time. So for complete description of mechanical state of a dynamical system, we must have to know the time dependence of qk and pk. Now in this introductory lecture, we will see the concept, two important concepts. The first one is the concept of phase space. So now I would like to give some details of phase space. One thing you must know that in Lagrangian formulation, motion of a system is described in a space which is called actually configuration space. And you know, configuration space is actually a 3n dimensional space if there is no holonomic constant imposed on the system, because if the system has n particles, then each particle has 3 degrees of freedom, and to describe a single particle, the space is three-dimensional, and if there are n particles in the system, then the space is 3n dimensional, and that space is actually formed by coordinates, or you may say position coordinates, and that such a space is called configuration space. But in Hamiltonian formulation, we deal the motion of a system in an space that is called phase space. Why this space is needed, how we will define this space, let us see these facts. Actually, you know, in Lagrangian formulation, there are 3n equations of motion of second order of a system of n particles in absence of holonomic system. You know, Lagrange equation. Lagrange equations. We write it as d dt del L by del qk dot minus del L by del qk, and this equal to 0. And here the subscript k means what? K is actually 1, 2, 3, so on up to f, where f is the degree of freedom. And if the system is not acted upon by any constant and the system contains n number of particles, then what is f? Then f is simply 3n. So you can see that this equation represents actually 3n equations in absence of holonomic constant. And at the same time, you may see that this is a second order differential equation. For general considerations, it is more convenient to write down 6n partial differential equation of the first order in place of 3n equations of second order. That will be convenient. So if we will write not 3n equations, but instead of 3n equations, if we will write 6n equations, and not of second order but of first order partial differential equation, then that will be more convenient. And for this purpose, there must be 6n degrees of freedom. And if the degrees of freedom will be 6n, you may say that the space will be of 6n dimensional space. And actually this 6n dimensional space is known as phase space, and sometimes it is also called gamma space. So you can say that the phase space is a 6n dimensional space. 6n dimensional space. Here n equal to what? N equal to number of particles of the system, and we have assumed that there is no holonomic constant imposed on our system. And this phase space is also, as I have told you, that phase space, or you may call it gamma space too. This is also called gamma space. Actually, in phase space, momenta are also regarded as independent variables like space coordinates. Or in other words, you can say that there is no distinction between the position and momentum coordinates in phase space. So, a single particle in phase space is specified by 6 coordinates. If we consider a single particle, that will be specified by 6 coordinates. You should note it. A single particle in phase space is specified by 6 coordinates. Specified by 6 coordinates. And among these 6 coordinates, there are 3 position coordinates, 3 position coordinates, and 3 momentum coordinates. Momentum coordinates. Actually, this 6-dimensional space is also known as mu space. Mu space. So you may call it this 6-dimensional space is called mu space. Mu space. And so we can say that a phase space or gamma space is actually a superposition of mu spaces. So you should note it that phase space or you may call it gamma space is actually a superposition of mu spaces. And so in brief, we can say that the phase space is a 6n-dimensional space formed by the generalized coordinates from q1 to q3n, that is 3n generalized coordinates, and the generalized momentum p1 to p3n. So we can say that a phase space is a 6n-dimensional space formed of coordinates q1, q2, so on, qk, so on, q3n. p1, P2, so on, Pk, so on, P3. So I hope you have understand the idea of phase space. Now we will deal in this introduction the most important concept of this topic, that is the meaning of Hamiltonian function h, or you may say simply Hamiltonian of the system. So Hamiltonian h. How we define Hamiltonian of a system, we will see first of all it, and after that we will learn about the equation of motion developed by Hamilton. You know actually that the Lagrangian of a system in general is a function of generalized coordinates and generalized momenta and time too. So we know in general Lagrangian of a system, which is denoted by L. We have already studied it, and this L is actually what? This is a function of Qk dot and T in general. Here K stands for 1, 2, 3, so on up to F. F is the degree of freedom of our system. And so if we want to find the total time derivative of this Lagrangian, so you can find it, that is dl dt, we can find it. As you see here, that L is not a function of only one variable, but it is actually the function of more than one variable. So we must follow the rules of partial differentiation to find the total time derivative of Lagrangian. And you have studied it previously so many times, so I hope that you will understand every step clearly. So first of all, we will differentiate L with respect to Qk. So what will be this? In brief, we write it as summation over K del L by del Qk, and as finally we have to differentiate with respect to T, so the second factor will be dqk by dt plus, now we will differentiate L with respect to Qk dot. So what will be this? This will be summation over K del L by del Qk dot, here is dot, and dqk dot by dt, and plus del L by del T dt by dt. And so what we can write this? See this, this will be actually Qk dot, this will be Qk double dot, because here we are differentiating Qk dot, and this dt will be 1. So we can simplify this result as summation over K del L by del Qk, this is Qk dot, plus summation over K del L by del Qk dot Qk double dot. And as dt is 1, so the last term is simply del L by del t. So you see that we have calculated the value of dl by dt. Let us say this is equation 1. Now actually I would like to find this factor del L by del Qk, and we can find it by the use of Lagrange equation. So the Lagrange equation, you know it, the Lagrange equation is what we will write Lagrange equation. Actually write Lagrange equation for a conservative system. You may see this will be actually del L by del Qk equal to d dt del L by del Qk dot. This is Lagrange equation. You know it. Now you can see that this del L by del Qk is equal to this much. We will replace this del L by del Qk in equation 1 from equation 2. So using equation 2, the equation 1 will be changed, and what it will become, we can write it. So using 2, equation 1 becomes, replace the term del L by del Qk from equation 2 in equation 1. So what will be our result? This will be simply, you may see the equation 1 and 2, dl by dt equal to summation over k d dt del L by del Qk dot Qk dot. You may see here I have replaced del L by del Qk by this factor from Lagrange equation, and plus the next terms, these are summation over k del L by del Qk dot Qk double dot, and plus del L by del t. Now we can simplify this equation as, actually these two terms may be written in combined form as this. How we can write it? We can write it as, this is d dt summation over k del L by del Qk dot plus del L by del t. You can check it. This is first function and this is second function. You can apply the rule of product of two functions for differentiation. So if we will operate this operator d dt on the first factor and take it out, you will get the first term. And now we will operate this operator d dt on Qk dot, that will be Qk double dot, and this will be left. So you can write the sum of these two terms like this. Now take this term in RHS into LHS. You may see we can write it d dt L minus summation over k del L by del qk dot and this equals del L by del t. Now this result, in this result, see this factor. As I have just mentioned the definition of generalized momentum, we know that del L by del qk dot is actually equal to pk, and this is generalized momentum. So replacing the factor del L by del qk dot by pk, what the above equation will become? So you can see simply this equation will become, so the above equation will become d dt L minus summation over k pk qk dot equal to del L by del t, and we may write it as d dt summation over k pk qk dot minus L equal to minus del L by del t. You may see it and say this is what will be the equation number. I have just written before equation number 2, so this will be equation number 3. This is equation 3. Now the function inside this square bracket is recognized as the Hamiltonian of the system, and we denote it by the symbol h. So this is recognized as Hamiltonian of our system. Hamiltonian H. So we can write this H is actually equal to what? This is summation over K pk qk dot minus L, and you may write L as a function of qk dot and t. So this is the basic meaning or basic definition of Hamiltonian of a system. You may define H in this way always. From this result, we can easily find that our Hamiltonian H is actually a function of generalized coordinates qk, generalized momenta pk, and possibly time t. So in general, you may write it in this way. Later on in the discussion, we will find that this Hamiltonian H will represent the total energy of our system in most of the dynamical problems, but not in all problems. Remember, we will see later in which condition this Hamiltonian H represents the total energy and when this does not represent the total energy. But In most of the dynamical problem, H represents actually the total mechanical energy, that is T plus V. You know T is kinetic energy and V is potential energy. But you will see the conditions under which this result holds. So these are some introductory facts of this topic, and after this we will learn the Hamilton's equations of motion, and after that we will learn its applications. So that's all for today.